So we were looking into, this differential amplifier, right? And then we had to, solve few problems based on this. Now, just to recall a few concepts, okay? Differential amplifier is basically where the inputs are provided with both inverting and the non-inverting terminals, okay? And these terminals do have their associated resistors, which is R1, R3, and R4, okay, towards the input side. And if we are talking about the gain, then it's wholly responsible with R1 and R2, right? So we saw a small mechanism where we can actually match up to these, resistor ratios, R4 by R3, which is equal to R2 by R1. So this resistor ratios we were maintaining. Why was that we were maintaining? So that we get this V minus is equal to V plus. Okay, so the voltages at the inverting terminal is equal to the voltages at the non-inverting terminal. So we, as much as possible, we try to make it equal, but practically speaking, it's not possible, right? So we had this small mechanism where we can change the value of resistance, and which directly impacts R4 by R3 and R2 by R1. So whereby I am able to equate the ratios of both of these resistors. Okay, so to say all the four resistors. So two ratio combinations, right? So I hope till this point we are very much clear. And we also looked into few formulas, right? V naught is equal to R2 by R1, which is multiplied by V2 minus V1. So with this, we get to know that, there's a difference between the input voltages. So hence the term difference amplifier. Sometimes it's already also referred to as differential amplifier. Okay. Right. So having all these basics in mind, okay, we had designed this modified circuit, okay, which can actually nullify the level shifting, okay, the level shifting. Right. So we will just look into an example, okay. Please keep your calculators and your notebook and your pencils, whatever, so that we'll just try to calculate these values and we will check if these values are proper. Okay. So the difference of two input signals is to be amplified by a factor of 37. So I get some information here, right? So what is this 37? It's referring to amplified by a factor of 37, which means it's referring to gain, right? Each input has a minimum amplitude of approximately 50 millivolts. So I also know that, I have around 50 millivolts for each input. Now, why is that they're saying each input? Because this is a difference amplifier. So we have to specify how much is it going to be for the non-inverting and inverting terminals. So here now, they are referring to LF353. Remember, it's not 741, it's LF353. So which means specifically you should know what kind of rules to apply. Okay, for 741, what kind of rules, and for 353, what kind of rules. So rules are nothing but, the input resistance, how much you're going to give, and, the values, okay, the values for currents. Okay, so all the bias currents, all this taken into consideration. So 353 OPAMP, design a suitable circuit and calculate the differential and common mode input resistance. So the problem is very straightforward. It's telling me what is RI diff and what is RI CM, right? So this is what we need to find out. Right. So usually what we do for LF353, right? What do? We usually take a high resistance, right? So I am taking this as 1 mega ohms, right? So we know that, as I was mentioning to you, R2 and R1 are very much related to the gain, right? R2 by R1, okay, is actually your closed loop gain, ACL, okay? So when I have this value, when I substitute this value, 1 mega ohms divided by R1 is equal to 37. ACL is equal to 37. How did I get that? I got that from the problem, 37. So can someone tell me if this value is correct? 27 kilo ohms. Are we able to get that? One M divided by 37.
Yes, sir. It is 27.027 kilo.
02. Fine. So yeah, we can take it as 27. That's fine then. Yeah. So the next part, we know that we are equating R3 to R1 and R4 to R4 and R2, right? So keeping that in mind, do you remember that which we had done the resistor ratios? So the same resistor ratios we are bringing it here. Okay, so keeping those resistor ratios in mind, okay, we now have the values of R1, R2, R3, R4. So it's just that if you find one resistor value, you're going to put that to the other resistor R1, R3, and then if you have R2, you're going to put it for R4. So as simple as it is. So this is the standard formula that we know. The differential amplifier, right? The input resistance, which is R1, R3, R4, right? So how much do we get approximately? Can you please add? So I think 27 plus 27 kilo ohms, that will give you about 5, 25, 6, 7, 50, 54 kilo ohms, if I'm not mistaken. Right? Yeah, 54 kilo ohms. So to this, if you add 1 mega, so this 54 kilo ohms is actually not going to have any impact, okay, because of the tolerances that we have in resistances, right? So approximately we take it as 1 mega ohms. So I think this value is right, isn't it? We're getting about 27. Yeah. Now we're getting this about 1 mega ohm. So this is very much negligible. So we take the standard value, which is 1 mega ohm. So the input differential amplifier, okay, the input resistance in differential mode is going to be 1 mega. So as we have discussed previously, we're going to add these values R1, R3, and R4, whatever resistances are there at the input side of OPAMP, right? So finally we get about approximately about 1 mega ohms. And we also know the formula for this, right? For common mode. We're just putting those formulas here. Since we have the values, R1 we have taken as 27, right? And that's going to be in parallel with 27 and 1 mega ohms. And please check and let me know if it is about 26.3. First, you can add them both, right? And then you'll have a value here. And then to this value, you can put 27K in parallel. Yes, are we able to get it?
Yes, sir. It is 26.29 or 26.
29, yeah, 29 is fine.
Yes, sir. Same.
So we'll take it as 0.3. Yeah. So the best thing, the best way to solve a problem, okay, is to find out what values are there which type of OPAMP they're referring to, and what formulas I'm going to use, right? So first, if you note down these things, then you will automatically know. See, for example, now I know that, R1 is equal to R2 by ACL. So since I have ACL and they're giving me a clue that, we are using LF353, so which means I know that I'm going to have my R2 as 1 mega ohm. So keeping these two values, I get R1. Now we all know that R1 should be equated with R3, right? So I get that resistor value as well. So similarly, since R2 I know, I will get R4. Then you have the formulas here, substitute the values and do a proper calculation. So approximately, that should be fine. You can see during your tests and examinations, you can either mention 1 mega ohm, or if you wish to, okay, you can add them also, and you can write another answer. That is fine. It's always nice to have more information than, using less information. That's fine. But if you want to, if you want to just put one value, then you have to really mention that this is an approximate value. Okay. I suggest that you write the full value, okay, so that you wouldn't have any confusion in that case. So can we proceed to the next problem?
So we are getting output is equal to 1 mega from the data sheet, isn't it?
Yeah, from the data sheet. See, usually what we do is, if you can recall, for some currents, we take some values like 500 nanoamps, right? So all these are from data sheets. So we actually want this to be high resistance, okay, R2 to be of high resistance. So we take it as 1 mega ohms. So you can keep this in mind, okay? If it is LF353, I'm going to take a high resistance, and high resistance, I'm going to take it as just 1 mega ohm. Okay, so few things you will have to remember, right? So that's why, in the question, extract data. Try to read the problem properly and try to extract data. At the end, once you have solved, it's always a good habit to go back to your question and read it again. Okay, so they have asked you to design, fine, we have done it. And remember, whenever design is asked, not just calculating these values, we expect you to actually draw the circuit, right? So I expect you to put the circuit and mention the values which we have just found out, right? It's very simple. You give a negative feedback, it's with a resistor, input has a resistor, inverting and non-inverting, and you have a R4 resistor. So just these resistor values, you can put it in your circuit. So that is actually called design. Okay, so that completes this problem, right? Design. And we have found out for both differential and common mode combination. Any doubts here, students?
No, sir, no doubts.
Okay, fine. So we'll see another example, okay, where we try to make some changes, okay, and we will try to use this modifying resistor, and we'll see how best that we can do it. So if you can understand this problem now, this example 2, okay, you will really understand what is the application of having a variable resistance, okay, of having, we have seen that, right? We have seen that previously here as to how important it is in nullifying, okay, nullifying the differences and making the resistor ratios to be proper. Modify the circuit designed in the previous example to give approximately equal resistance at 2 input terminals and to provide output voltage nulling. Now this is very important, right? Now they are telling us to get provide output voltage nulling. So this is a very key differentiating factor which gives us a clue that I am going to put this extra circuitry not only R4, but I'm going to have RF and RV, a variable resistance and a feedback resistance, right? RF, a fixed resistance, okay, RF, right? So let us see one by one, and we'll see what best that we can do. Now, using the previous problem, we actually extract those data R1 we got, R2 we got, okay, and we know that R3 plus R4, okay, R3 plus R4 is equal to R1, okay, which is also equal to 27 kilo ohms. So this is from the previous problem, and now we are going to take this ratio, okay, we are going to take this ratio, and we understand that R4 by R3 is equal to R2 by R1. So we have these values here, right? We have these values. When you substitute those values, just check if you're getting about 37 R4, okay, R4 by R3 is equal to R2 by R1, okay, just take R2 by R1, you have R2 value, you have R1 value. So try to divide this 1 mega divided by 27. Just check if you're getting about 37. One mega divided by 27.
Yes, sir. 37.03.
Yeah, so we will take it as 37. Fine. So this is verified. Now I know that R4 by R3 is equal to 37. Now the reason why I'm very much concerned with R4 is because that is where I'm going to put my variable resistance here. So I'm very much interested in finding out the value of R4. So now R4 is equal to R3 into 37. I just cross multiply here, right? So 37 times of R3. Okay. Now what we will do is we will use two equations. Okay, we will use this first equation and we will use the second equation. So wherever R4 is there, I'll be replacing it by 37 times of R3. So this becomes R3 plus 37 times R3, which is equal to 27 kilo ohms. So which means, I can take 1 plus 37 here, okay, and bring it to the denominator, and 27 divided by 1 plus 37. So check, are we getting about 710 ohms? So 27k divided by 38.
Yes, sir. 710.52.
710 ohms, right? So we don't have standard 710. Okay, so what we do is we use 680. Okay, 680 ohms. So that gives us a standard value. So we will be considering 680 because right now what we are doing is we are designing. So which means we are looking at the practicality. So for my calculation, I wouldn't be using 710, but then I will be using 680. Right? So we know that R4 is equal to 37 times of R3. So 37 into 680. Okay. So tell me if we are getting 25.2.
Yes, sir. 25.16.
So we'll approximate it to 0.2. Fine. So here now again, this is important, the tolerance, okay, plus or minus 10%, okay, of tolerance for the resistor is important for calculating, so that I get to know what is the minimum and what is the maximum that it can go for. So this 25.2, okay, now I'm going to calculate the maximum value. So I make it 10%. So 10%, is approximately like 2.5 kilo ohms, right? So 2.5 plus 25, so it should give me about 27.7, right? So R4's maximum value is going to be 27.7. It can go up to 27 because of the tolerance. And the variable portion now. So this variable resistance that we are going to put is about 20% of the maximum value of R4. So that's the thumb rule. Okay, thumb rule is I'm going to have RV in such a way that it is 20% of the maximum value that R4 can attain. Now the value of R4 is not important, but R4 max is important. Why is this R4 max important? Because I am taking the 10% plus or minus 10% tolerance also into consideration, because practically we have to think about it. So R4 max is what we are talking about. Okay, so 20% of not R4 but 20% of R4 max. Okay, so if I take 20% of that, please check and tell me if you're getting about 5K. So how do you calculate 20% of 27.7? So you multiply 27.7 multiplied by 20%. Right. So I think you should be getting about 5.54, if I'm not mistaken.
Yes, sir, 5.5.
54. Yeah. So that's why, approximately we're going to use 5 kilo ohms. Okay, because that's the standard, and I'll be omitting this 0.54 kilo ohms. Okay, right. So approximately 5 kilo ohms is going to be my value of RV. Okay, this RV, variable resistance. Right. So the fixed portion of R4 is, okay, so how much is going to be fixed? So which means R4 max minus RV. Okay, so the maximum value minus the variable resistance value. So which means I'm going to have 27.7 is the maximum that it can go, minus the variable part here. Okay, so this variable part, this 5 kilo ohms, I bring it down here, and approximately, I am getting about 22.7. Okay, 22.7. So this is going to be the practical value of RF. Okay, and since I do not have 0.7, okay, 22.7, I'll be using 22 kilo ohms. Right. So what we're going to do, we're going to have RF. Okay, so that is given here as 22 kilo ohms. Right. RV, I put it as 5 kilo ohms. Right. R1 we have calculated previously. Right. And R2 we have taken from the previous problem, right? Or the standard value, which is going to be 1 mega ohms, right? So based on all these calculations, okay, and yeah, 680 we have found out from here, right? So based on all this, we try to design, and finally we put the circuit here. Okay, so in the problem, okay, we will mention, I'm going to mention that, use a 741, use this amplifier. Okay, and accordingly we will proceed in our question paper, right? And this is one example, okay, of a computer analysis of a differential amplifier. Okay, where you can see that 680 is here, 27 is here, the same thing done with the help of computer. And R4, okay, R4 is calculated here. It's taking about 25.2, yeah, 25.2, right? And yeah, the same thing here, 1 mega ohms, so 1000K, the same thing using computer. So students, any doubts here? Only thing is, concept wise you should be very clear, fundamentals you should be very clear. What is inverting, what is non-inverting, what is a feedback, what is a negative feedback, okay, what is summer, where I'm going to give the inputs, difference amplifier, where are the inputs given, R1 where I'm going to give, R2, R3, R4 where I'm going to give, where is the feedback given, okay, and what is the output voltages, and what are the input terminals. If I have to calculate input differential amplifier, input resistance in a differential mode, then what is going to be the formula? If I'm going to calculate resistance at the input with common mode configuration, then what is going to be the value? So all this, okay, should be in your mind. And few standard values, okay, like 1 mega ohms, okay, so all these standard values should be kept in mind. One small thing that you need to remember here is always take the R4's maximum value. How you will get the maximum value? Based on the tolerance, okay, plus or minus 10% is always taken as standard, okay, and RV is going to be 20%. So remember, 10% for tolerance, 20% for variable resistance, okay, both are taking R4 into consideration, right? So R4 you calculate, R4 max you calculate, RV you have, and RF, okay, the maximum value minus RV. Okay, so this is how we try to calculate, okay, the values and design an OPAMP. Any doubts here, students?
No, sir.
Okay, so with this, we actually complete module 1. Okay, and we will be moving on to the second module, okay, which is going to be based on the AC amplifiers. Okay, so just a moment. So are you all able to see the screen?
Yes.
Yeah, fine. So this is our second module, which is going to be OPAMP as AC amplifiers. Okay, so I've just put a small internal diagram of an OPAMP here, where we are talking about plus voltage, minus voltage, okay, the inverting, non-inverting terminals, and G into V. These are all equivalent circuits internally. Okay, fine. So now we are going to talk about AC, so which means we need something to block DC. Okay, so we are going to use capacitors for that work. Okay, so capacitors are going to help us in blocking DC, and these are going to be called as AC amplifiers. Okay, because capacitors helps us in blocking DC. OPAMP circuits can readily be capacitor coupled. Okay, I will be using the term CC. Okay, capacitor coupled CC. Many times we'll be looking into this term CC. Okay, so I will be using CC as the short form. Okay, it can readily be capacitor coupled at the input and output so that they operate as AC amplifiers. Now this is important. Okay, how do they become AC amplifiers? With the help of capacitor coupled. Okay, with the help of capacitor coupled inputs and outputs. So at the input, how we are going to put a capacitor, and at the output side, how we are going to put a capacitor. Fine. Capacitors must not be allowed to interrupt the bias current paths to the OPAMP input terminals. So it should not interrupt. So capacitor should block voltages, and it should be able to pass through the bias current. So bias currents is actually making your circuit more stable. This requires additional bias resistors, which can affect the circuit input impedance. Now we have learned that the input impedance is very high, isn't it? Wherein the currents are all blocked. But at this point of time, when we are using these capacitors, okay, we make sure that small amount of current can pass through. So these are bias currents. Since capacitors have their highest impedances at lowest signal frequency, keep this in mind, this is important. Capacitors have highest impedances at lower frequency. So less frequency, high impedance. So frequency and impedance inversely proportional with respect to capacitors. All coupling capacitor values are calculated at the desired lower cutoff frequency. So you have when you talk about a bandwidth, you have a higher higher level of frequency and a lower level of frequency. So when you minus them both, okay, so you're going to get a range of frequencies. So that is nothing but your bandwidth, okay, the bandwidth or the series or the frequencies in which it can operate. So here, okay, when we are talking about coupling capacitors, Okay, we take low cutoff frequency into consideration. Okay, because at the lowest, we get high impedances at the lowest frequency, so that is important. The impedance of these coupling capacitors at F1, which is some lower cutoff frequency, is usually determined as 1/10 of a resistance in series with the capacitor. So I'll be having the value of resistance, which is 1/10 the value. Okay, if I'm operating the capacitor at frequency F1. What is F1 here? Lower cutoff frequency. Okay, lower cutoff frequency. The largest capacitor in a circuit is normally selected to set F1 for the circuit, and in this case the capacitive impedance is made equal to the series connected resistance. Now remember this 1/10 of the resistance that I was talking to you about, right? So this is made equal to to the impedance of capacitor. Okay, so it is a kind of nullifying effect. It's a kind of nullifying effect. So that's why you can see here the impedance of these coupling capacitors at lower frequency, lower cutoff frequency, is usually determined as 1/10 of resistance in series. So whatever resistance that you are taking, 1/10 value of that is going to be the impedance of the capacitor, right? Okay, so major important thing that you need to consider here is op-amps can be made AC ready if and only if we have these capacitors. Okay, so if we have capacitors, then it's going to be AC ready. So how are they AC ready? Because they're going to block DC. Okay. So students, any doubts in this? Can I proceed? Here, any doubts?
Yes,
okay, fine. Right, so this is your circuit for capacitor coupled voltage. Okay, so this is the main thing that we will be actually focusing on. Okay, this is the main thing here. Yeah, capacitor coupled voltage follower circuit. Yeah, so as you can see here, we have a capacitor which is C1, okay, at the input side, and we have another capacitor C2. Now the shape, the shape is like this, okay, where it has a C and then a straight line. So this usually refers to the coupling capacitors. Okay, right, and we have seen these values also. Input impedance, okay, R1. Okay, so this is the resistance that I was talking to you about, the R1 resistance. Fine, so let's get into the details. Okay. When a voltage follower is to have its input and output capacitor coupled, the non-inverting input terminal must be grounded via resistor. So this is the basic rule. You need to have a grounded resistor, and that should be connected at non-inverting terminal. Non-inverting terminal, okay, a resistor connected to ground. Okay, if and only if you need to have capacitors at the input and output side. This is the rule. Okay, the resistor is required to pass bias current to the amplifier non-inverting input terminal. Now, why was that rule made? So that there can be some amount of bias current. Remember IB, we spoke about IB max. Okay, we had some 500, 580, 590 nanoamps. Remember, so in the data sheets. So this IB is possible only when I put a resistor here connected to the non-inverting terminal to the ground level. Okay, so with the help of these resistor, okay, this resistor, I'm going to generate something called IB. IB is your bias current. A resistor equal to R1 can be included in series with the inverting terminal. Okay, so I can probably include one resistor here, okay, in the inverting terminal so as to combat the losses. Now I have loss because of this, right, which is, you know, IB into RB. Okay, so IB into RB, there's going to be a loss here. So in order to combat the loss because of this resistance, I can put another resistance here because this is going to work in the opposite direction. So here loss is going to help me in getting a gain in the other terminal. So this resistor, okay, the resistor because which is connected here to the non-inverting terminal, okay, is going to cause a loss. So in order to combat that, what I'm going to do, we have chances of connecting another resistor here, okay, and that is going to help us in combating the losses because of this, right? Okay. In case of a circuit with its output capacitor coupled, small DC offset output voltage are unimportant because they are blocked by the capacitor. Okay, so whatever capacitor that you're going to see here, okay, towards the output side, this capacitor towards the just a moment, yeah, this capacitor that you're seeing towards the output side, so they block. Okay, so which means whatever, you know, small kind of you know, offset voltages that you see, you know, that will be nullified with the help of this capacitor. So which means we are using this capacitor to function, to make our amplifiers function as AC amplifiers. Okay, fine. Now if you can see this diagram here, right, so in this diagram we are talking about the impedance of the capacitor. Okay, impedance of capacitor and the impedance of second capacitor. So our design is usually involving, you know, designing the C1, C2, okay, and what is going to be my load resistance, what is going to be my R1. So having all this in mind, okay, we can actually design a capacitor coupled voltage follower. Okay, so moving on to the next concept here, I have brought the circuit back, okay, and it will be easy for us to, you know, understand, right? So design of capacitor coupled follower involves the calculation of, as I mentioned, we're going to use R1, C1, okay, and C2. So basically these three, once we have these three values, okay, then it's going to be easy for us to design capacitor coupled voltage follower. Okay, the reason why we use voltage follower is because whatever input voltages that we are giving, okay, the same thing, the output, okay, follows the input, right? As always, the largest possible resistor values are normally selected to ensure minimum circuit power dissipation and minimum current demand from the power supply. So we use large resistance, okay, we use a large resistance so that less currents can actually pass through. Okay, if you can recall, we were using about 1 mega ohms, right, in one of our OPAMP configurations. So that's a substantially high resistance. Okay, so if there is less current that passes through, okay, then there's going to be less power dissipation. Can someone tell me what is this power dissipation?
Exiting of the power, like going out.
Okay, that is also fine. Now, this power dissipation is normally, treated as heat. Okay. When let's take your laptops, for example. Okay, your laptop's CPU gets into a lot of operations. Okay, so in order to combat that, there's a fan that is connected to the CPU, okay, to the processor. So why is this fan connected? So that all the hot air is exhausted. Okay, so there's a lot of power that gets dissipated, okay, because it is not only just displaying whatever presentation that we are doing, but then there is hundreds and hundreds of processes that are happening behind the screen. Okay, if you can just go into the alt control delete mode, okay, wherein you can actually see how many processes, how many threads, okay, what are all the requests that is happening. So all this, right? So when we talk about our circuit, okay, our circuit also will dissipate power. Okay, so P is nothing but V into I cos theta. I think you have studied this in your basic electricals, probably, right? So because of this voltages and currents, okay, there's going to be power dissipation. And most of the time, that's going to be in the form of heat. And if you can see, are we using the same processors which are used in laptops and cell phones? Is it possible to use the same processor?
No, sir.
Not possible. Why is it not possible? Because the usage, okay, that is for a laptop is higher. Okay, the power required for a laptop is higher. We have designed, we generally use phones, okay, so that it at least gives us a backup of a day or more than that, right? So if I can just use it for 2 hours or say 1.5 hours, will I really want to purchase the cell phone? I don't think so, right? So of course there are a lot of operations happening in the cell phone as well, but then those are less power hungry. Okay, they do not consume more power. Okay, so our circuits are designed in such a way that if I increase the resistor values, then the currents that are passing through are going to be less. So if the currents are being less, then the power dissipation is going to be less. If this is less, then ultimately I need to take less power supply. Okay, so it's all with the current and voltages. Okay, so once we can control these currents and voltages, okay, it's only then we can proceed to less demand of power. Now I think you would have heard of all these processor generations, right? 8 gen, 9 gen, 10 gen, 11 gen. So what is this happening exactly? So they are trying to include more transistors in their processor. Okay, so any processor for that matter, okay, we have Intel, we have ARM based processor, right? So any company for that matter, they try to always get their next processor much better than the previous one, right? So how do they do it? They pack more transistors inside them so that more functionalities are included, and they consume less power. So by this, what is going to happen? If your laptop is suppose now giving you about 3 to 4 hours, it will suddenly spike up to about 8 hours, just because the power requirement is less, and there is space for huge battery. So that by the time that battery gets over, you get an ample amount of time, a day's juice that you need for working with your laptop. So if I have this resistance values to be higher, okay, then that means I'm going to use less, that's impacting less power dissipation, and the impact is less power supply. Okay, the smallest possible capacitor values are normally used for their small physical size and low cost. Okay, so usually to to manufacture a capacitor, it takes a lot of time. Okay, it takes a lot of time and effort, and it is not as easy as fabricating a resistor. So instead, what I'm going to do, I'm going to increase the resistor value and decrease the capacitor value so that I can cut short on the cost. Okay, I do not want to have my circuit to be too costly because I need to sell it to the vendors, right? Okay, so keep in mind the smallest possible capacitor values are taken just because of the size and cost. Okay, these two are important. The minimum value, the maximum value for R1 for a bipolar op-amps is determined as 0.1 VBE divided by IB max. So how much ever is your maximum biasing current? Okay, so that one and the voltage between your base and emitter. So 0.1 times. So this one was actually previously derived, and we are just using that value here. Okay, so I think we probably stop here. Okay, and I will continue with the upcoming concepts which are dealing with this voltage follower. Okay, so we are going to see a small derivation, okay, as to how I'm going to calculate C1, okay, and how am I going to calculate C2. Okay, we are going to use the C1, we're going to use C2 in many of our problems, and these two are the major capacitors that we are going to talk about, and we'll also see a few problems. Right, is that clear, students, with whatever was discussed today? Any doubts, any questions? Was it all fine? Have you understood?
Yes, sir.
Okay.